All right, let's get started. Hi, everyone. I hope you guys had a good lunch today. Let's thank our sponsors. Good enough. All right. Today, I'm going to talk about the personalization platform that we built based on the Lambda architecture. My name is Seo Wee. I'm running the personalization team at Trulia. And here today, I have Sotos Matsunas on the stage with me, who is the tech lead for the project, the real brain behind the project, so to speak. So before we jump into the Lambda architecture, I want to also share a little bit about the Trulia, what kind of problem we are solving. Before we dive into how many of you have struggled in finding homes to live, either for rent or to buy? Anyone struggled, had the same issue? Yeah, right? That's the problem that we want to solve together and we want to make the process more easy and more enjoyable by providing the data and the insights so that you can make the best decision. So when we say we want you to make a best decision, the best decision is not about finding the best home in town, but the best decision is finding the best home for you. So for our business, it is so critical to understand our consumers individually. That's why we built the personalization team. So our team is about a year plus old with about 6 engineers so far. We are hiring. And so our team collects all the consumers' event data. We process them. We build the digital signature of each individual users. We call user trait. And based on that user trait, we personalize your experience on Trulia by sending the relevant content through the email or push notification or personalized experience when you're on site. So when I say user trait, what that exactly looks like. First of all, we need to address that person. So there's a user ID for the ones who registered to Trulia. But there are a vast majority of users who are not registered. So for those users, we at least know something we call secondary ID. The examples are the browser cookies when they come through the browsers, or device ID when they come through us, come to us through the mobile native apps. And then on top of that, we have some factual events that this user performed. To begin with, what kind of search query this user ran on our site, what kind of homes this user visited, what kind of homes this user shared or saved, so on and so forth, because they are very strong signal about what this user is looking for. And then based on those factual events, we try to answer one level up questions, such as, what kind of user this is. Either this user is a renter or buyer, which location this user is looking into, what's the price range, whether this person is looking for the single family house or condo or apartment, kind of. So that's what we call the user preference. And then this is common for the audience in this room that when we know something about the user and we have inventory, then obviously we have the recommended properties. So the home set that we want to recommend for each individual users. So how do you build this user trait? There's nothing much of top secret here. It is just collecting all those events as we all do, process, toss it up and down, and run some data science model around it, and then boom, there was a user trait. For those user trait, the way that we can process it is, I would say there are two extreme models. One is a batch-oriented models, where we run the batch cycle, where we process all the events all at once, and then that batch cycle runs hours, and then at the end, it generates a dump of user traits for entire user base that we have. Which is easy, especially now we have Hadoop and we have Spark, and for the people in this room, this is our bread and butter every day. But the things that we are missing there is we lose the opportunity to learn about the consumer's activity that happened just 2 seconds ago, which can tell us a lot, especially when that user is new users. So another extreme of this processing is real-time processing, event by event, streaming, and we had all those like cool keywords like in real-time analytics. We talked about it a lot, especially last Hadoop Summit. There we meet some challenges. The typical challenge is we lose the opportunity to learn about new dimension or new metric for the user who went to Trulia before, and when the events is already streamed through. And whenever we have bugs in our code base, which is typical, then it's so hard to fix that bug and fix the damage that they already made on our user trait data that we already processed through the streaming processing. And also, obviously, there's a tracking bugs, so the data quality or dirty data, dirty tracking data is always there. So it's so extremely hard to make a fix for those kind of events when we have only real-time processing layer. So we looked around what can be our solution for those two type of access patterns. And then we looked around and we settled down to the Lambda architecture. So Lambda architecture has batch layer and a real-time layer, and we merge them when we serve the data. So we have opportunity to recalculate the full user trait from the full event body at scale almost at every batch cycle. And we load that into the NoSQL database so that we can read out of that user trait in interactive latency. And whenever we come up with new metrics to add, it's just a matter of adding the code base and test it, deploy it, and at the end of the next batch cycle, the new metrics there for the entire user base. So easy. And then through the real-time layer where we only calculate the delta part of it that happened during the daytime, we merge it when we are serving it. So we took the conventional wisdom. The beauty of the Lambda architecture is you don't need to deploy everything all at once. You start with a batch layer, build it, and you build a serving layer, and you launch your MVP use case. And then you catch up with the real time, and then the all real complexity or real fun starts when you now think about how to merge this real-time view and the batch view. So on that part, I want to open the stage for Sotos.
Great. Thank you, Seuk. So my name is Sotos Manzanas, and in the next few slides, I'm going to share with you how we implemented our version of the Lambda architecture, what our specific needs are, and what complications we faced. So, there we go. But first, let me share you of how the whole architecture looks like, and I'm mostly going to focus on the upper arc, the real time. But first, let me explain a bit of how we built the lower part, the batch layer. So as Seuk said, we accept user actions or events in our lingo. And events are JSON documents of a specific format. So we start by accepting events on a RESTful web service, which we call the event API. And there we validate and reject all the events that do not adhere to our formats. From there, we pipe them to a Kafka queue. And then we use KMU to write the events on HDFS. And once we write the events on HDFS, they become part of our immutable, append-only event master dataset. From there, once a day, a little bit after midnight, we start our batch process. So it's a very complicated Hadoop workflow written in Scalding and Scala. And it processes every single event we've collected since the beginning of time. And for us, the beginning of time is about a year and a half ago, up to the last second of yesterday. So up to 11:59 of the day before. And then it basically starts running our batch process. Once the batch process, the batch workflow is done, we have full user traits for pretty much every user, registered or unregistered, that we've seen for the last year and a half. And we store the user trait as a JSON document on an HBase database. For the real-time part, as soon as the batch workflow starts, we also spawn a storm topology that pretty much does the same or similar thing to the batch, but only on the events that have come to our platform from midnight onwards. And once the real time is done, and we'll go through how this is done in the next few slides, then we are ready to serve the newly calculated user traits from our serving layer. And we do that through another RESTful web service, which we call the user trait API. So what the user trait API does is it looks up the user trait on HBase, looks to see if we have anything for that user in the real-time layer, and then merges the two and serves it to our clients. So we call this combination of batch process plus a storm topology an epoch in our lingo. And once this epoch is done, then we're basically able to retire the old epoch and start serving through the serving layer through the new epoch. And I'm going to explain how these transitions go on in a subsequent slide. Sorry, it's not moving. There we go. So before I explain to you how we designed a real-time layer and why it's so complicated for us, let me explain our user model. As Hadoop mentioned, we support both registered and unregistered users. So no matter if you come to our site as a logged-in user or not, we will create a user trait for you. So obviously, the registered users have a unique user ID, but unregistered users have what we call a secondary ID. It's basically the path through which you came to our platform. And this path can be the web, mobile apps, or an email address in case you first came to our platform through opening like a recommendation email. So registered users have one unique user ID and one or more secondary IDs, whereas unregistered users only have one secondary ID. So we call this association of user ID to secondary IDs a user linkage. And we discover user linkages through our batch process. So while the batch process is running, it basically associates user IDs to a set of secondary IDs and saves them on a different table on HBase. And our job is to make sure that we link and merge all user activity correctly, no matter what device or what path they came to our site. So what complicates our case? As I said, we discover the user linkage while the batch workflow is being run. But at the same time, we have a real-time storm topology going on. So the only thing that this real-time topology knows is the linkages we discovered yesterday from the previous run. But linkages may change from day to day. We may discover new linkages, or we may discover that what we thought was a linkage from user A to secondary ID B has now changed, and user A is actually linked to secondary IDs C, D, and E. So, and we also have one more case where a new user may log in right now. So this user login and this user linkage is only reflected in the real-time layer and not in the batch layer. So we need to plan for all these events and all these complications and make sure that the user trait we present to our clients through our serving layer reflects the state of the user as of right now, not as of yesterday. So if we had a very simple case, our Lambda implementation of the real-time layer would look like this. We would accept events through Kafka spouts. We would parse and validate the events through a parse pod. We would look up the user IDs for secondary IDs through what we thought was the source of truth, basically a table on HBase. And then we would store the partial user traits on a mem database, and in our case, we use Redis. And we would use user ID, the user ID we discovered from the previous step in the linkage lookup, to store that partial user trait with that user ID as the key. But as I said, we have more complications. Our case is not as simple as that. So here's how we do it. So this is our current real-time design. So we still start with a Kafka spout, and we pipe all the events for today through that. Again, we parse the JSON document and reject events that are not valid. But for the linkage, the only source of truth we have as of right now is yesterday's lookup. So we use that because that's the best we can do as of right now. So how do we store the partial user trait now? I mean, we found the user ID, but this may change at any point. So when we decide to store it, we actually store it twice. Once by secondary ID and once by user ID, in case we need to change the linkage between the two. So at some point, the batch workflow finishes, and we now have a new set of user linkages. So what we do as the last step of the batch workflow is we run a delta job. And the delta job calculates what linkage has changed from yesterday to today, and also gives us any new linkages that appear today but did not exist yesterday. And we pipe the results of the delta job through a different spout, which we call the control event spout. So we pipe lookup changes that for us look like regular events, but they're of a special type called the control event. And we pipe them through a different bolt that only gets activated when the batch finishes, which is called the control bolt. So the control bolt has two jobs. One, it has to notify the linkage lookup bolt that there's a new table available for lookups. So the linkage lookup bolt has to immediately switch to the new table. And the second job of the control bolt is to get every single user ID and every single secondary ID we've seen today and pipe them back as control events to our regular queue. So it pipes every single user we've seen today plus the results of the delta job as regular events through our regular Kafka event spout. So these events go through a regular parsing phase. Now, the linkage lookup bolt has been instructed to switch to today's lookup. So it's going to look up it's going to find out the correct linkage for all these user IDs and all the secondary IDs we pipe through it. So now we're ready to do our actual work. So we call this the rebalance of the user ID. So what we do is that in case a user ID is now mapped to a different set of secondary IDs than we thought before, we erase it from Redis. We grab all the partial secondary user IDs we now know are associated to that user ID. We create a new user trait, and we store it in Redis. And now it's actually the correct state for that user as of right now. So I talked about epochs and how we transition from epoch to epoch. Like, when do we signal to our clients that it's now time to start serving from a new table and a new set of keys from Redis? So we consider an epoch to be done and ready when the rebalance, the process I described in the previous slide, is complete. And for us, it's not a perfect algorithm, but for us, the completion of rebalance is when we have seen no new user ID coming through our pipeline for at least 30 seconds. So we consider that basically the control bolt has piped everything it has to pipe through the Kafka event spout, and the other bolts have done their job for everybody. And how do we do that? We basically have a very special Redis key with a time to live of about 60 seconds, basically double the time of 30 seconds. So every time the storage bolt sees a new user ID that it has to rebalance, it writes to that key. And by writing to that key, it updates the time to live to a new 60-second period. So once we see that this key disappears, and we check it once every few seconds, then we know our rebalance is done, and we're ready to serve a new epoch. So let's see how it works in a timeline kind of fashion. So as I said, we collect events from the beginning of time up until now. So when midnight comes, we start the batch layer for the current epoch that we want to calculate, and we call it the epoch n. At the same time, though, we have new events coming to our platform. So we call those the speed layer events for the same epoch. And to pick up the slack for those, to pick up the delta, we start a new storm topology, and we call this the real-time layer for epoch n. At some point, after a few hours, the batch layer is done. So now we run our delta job, and that kicks off the rebalance in the real-time layer for epoch n. When this is done, then we know the new epoch is ready to be served. So we basically notify all our clients, and our serving layer now starts serving from the correct tables and the correct keys from Redis. And the next day, basically, we have the same series of events. New events come in, a new batch layer starts calculated, new events for real time, a new storm topology is being spawned. So at that point, we have two parallel storm topologies running, one serving and one calculating. And on when the rebalance is done, then basically we can now start serving from n+1. And at that point, we're ready to stop the topology, the real-time topology for epoch n. So at this point, we only have one real-time that's actually processing and serving at the same time. So let me share a bit about our input and what we're currently processing. So we're processing hundreds of millions of events per day. That translates to billions of events per month. And our current event master dataset is about 12 terabytes. Out of those events, we calculate a few hundreds of millions of user trades daily, and a few dozen millions of user trades in real time. So what did we get by implementing Lambda? So we're able to continuously add features as we please. We're able to fix our bugs by going back in time, and we can retroactively apply the new features we implement on all data. And what we created is this virtuous cycle of learning more about our users, having our users interact more with us, and through those interactions, we learn even more about them. And by doing that, we were able to enable our clients who use our user trades to help our consumers make the best decision during their home search for them. So that's it. These are our email addresses in case you have any questions. Or if we have anything. Sure.
Did you consider a graph architecture for this instead of a Lambda?
We did not.
Any reason, or just
Graph architecture.
graph database?
Graph database.
Yeah. So graph database part, the question was whether we consider the graph database. So graph database part can help us in the linkage part and when we merge the user traits, but it doesn't solve the part that where we have like billions of events coming in and then be able to process them to make a user trait there. So it will be very useful to merge user traits, but that was a small part of it, and we didn't want to introduce another infrastructure there.
What do you use for the rebalancing effort? Is it just that Storm bolt is handling all that processing and getting the last day's data, or is it something else on the side like a map restructure?
No, it's actually it's a bolt within the same topology. So we try to simplify the architecture and use the exact same topology to do the whole rebalance. Yeah, and we try to also use the same spouts when we pass the control events back to the same spouts.
How do you manage to handle the duplicate gates if the event is being processed?
In the events. The question was how do we handle the duplicate events? Each event, we put the event ID, and that's what we use to identify whether these two events are duplicates or not. And that is very good practice to embrace when you want to build the master event data set.
And you'll be looking at the event ID every time when you encounter an event?
Yes, we use kind of techniques that duplicate events should have the same event time ID, same event time. So we kind of sort the events in the event time order, and then those duplicate should come back to back for the most of the time. So that's kind of heuristic that we use, but
How many different types of identifiers were you mapping?
Excuse me?
How many different types of identifiers were you mapping? Just one, or is it?
We have multiple. The question was how many different identifiers for the user that we use. We use browser cookies, we use mobile device IDs, we use email address, and so on and so forth. And then those are the ones that we are using now, but it's going to keep growing. Like for example, the phone number could be another one, or the Facebook ID token could be another one, so on and so forth.
How close are you to doing real time?
We're
We're using it in real time.
at most a few seconds delay, at most. We're usually sub-second. Yeah. So, yeah.
So do you differentiate hobby users or code users, especially those people who are right now in the market to look for rent or sell or buy or
Yes, well, we have a data science model that classifies users on a scale from 0 to 1 as a renter or buyer. And it's,
I think you see it reflect in your user trait or profile.
we assign a user score, user type score. So every user has a score from 0 to 0.99 or 1 actually, with 1 being a buyer and 0 being a renter. And it's pretty, it's fairly accurate actually. Yeah. So if you go back to the,
Yeah, I saw that one, but I
Right.
don't know whether it reflects the current user's demands or it's a historic score.
it changes day by day. Yeah. So it's not static. It depends on your direction. So you may switch from render to buyer, or you can be both actually. Yeah.
Yeah, when user registered with us, we ask questions, and there's an explicit signal from the user. But also, renter yesterday becomes buyer today, and then people don't update their profile diligently. So also we take into account of a lot of behavioral signals there as well.
So like the user type and the recommended properties, those delivered as traits as a result of the batch process?
Both the result of the batch process and in real time.
So how do you modify them in real time? Are you delivering all the information that was used to calculate it to begin with, so the same algorithm is applied?
So the idea is that we're moving towards that. Right now, it's not everything, especially with things that you need like a very long period of events to calculate. But we're getting very close to that as well. Yeah.
So
The idea is that you would deliver the result of the batch process as well as the features that you need to actually rescore in real time, the pieces that you need.
Right, exactly. So we want to do that, but we're not quite there yet, but that's the plan.
So
To have a real-time rescoring module as well.
the trick that we are employing there is we kind of decoupled from the fact aggregation part of the storm topology and the scoring part of the real-time processing. So that in this fact aggregation part of the topology, it says, oh, for this user, now is good idea to refresh his score, and then it sends a signal to the data science model side. And then data science model side actually read not only the delta of the day, but also it is batch view as well. To see that person as a whole user trait, and then recalculate the score there.
Your batch accessibility in between runs, is that just maintained forever? So like you have a batch that ran at midnight yesterday, and then you run another one, so you still have basically the data set at any point in time. Is that accurate? You completely replace the batch.
We completely recalculate the user trait every day. So once the new output of the new epoch batch comes out, then old epoch get discarded.
The structure of the input JSON, is it same, is it standard for regions, countries?
Well, we only operate in the US right now, so it's, yeah.
And then this JSON model take it as sort of like pseudocode,
Yeah.
not the exact JSON model, please.
What do you use for your batch process itself, like the technology?
We use Scalding and Scala for batch, yeah.
And does that run on? Do you employ Yarn at all with that?
It runs on Yarn, yes. 2.6, I think.
I forgot
I think
the
it's
version.
2.6,
Yeah.
yeah.
Could y'all cover the architecture with us of everything? Are you using Kafka, Scala, and
A Storm as well, yeah.
Kafka Storm,
HBase,
Hadoop,
Redis.
HBase, Redis.
Did you see any overlap between Kafka and Storm, or did they naturally? I mean, did you have to make design decisions about what to do with Kafka versus?
I think they work very well together. It worked right out of the box for us.
At a very high level, Kafka is a queue where you put the events, and then Storm is the one that you take out the events and process it. So we don't do the processing inside of Kafka.
Using the core version of the Storm, like Trident version.
Excuse me?
Are you using the core Storm or the Trident Storm?
No, just the simple Storm. No Trident. Yeah.
Is there some reason y'all went with Storm instead of Flink? Or one of the others that do a little better with real time? Maybe it just wasn't quite there yet when y'all started?
Yeah, around the time that we started this project, especially the real-time side, Flink was not there.
Yeah, and we also need like very fine control over each and every event, especially for the rebalance part. So Flink kind of like bundles everything together, and at least I couldn't figure out a way to like pick a specific event out of that like windowing. But again, we didn't look too much into it, and it was very early. Yeah. Yes, absolutely. Yeah, sure.
Not with control on this.
All right. Thank you. Oh, sorry, one more. All right.
So how do you handle the cookie churning? Because browser cookie churns a lot, and how do you kind of keep the history and do the rebalancing in your pipeline?
Cookie churns have like multiple aspects of it. One is, for the same user, the user keep like clearing his cookies. So one user has like multiple or actually many of the cookie values. That's totally fine for us. We from day one we built the user trade having cross-platform in mind. So for us, it's just another another browser or another platform that this user is coming from. The tricky part is when multiple people share the same browser. So one browser cookie maps into the multiple users. Like you have husband and wife and using the same browser, but they keep like logging in and out with different credentials. That sometimes make things a little tricky. We did some data analysis like to see how big of this problem is, and it was actually like less than 0.1% of our user base. So we made the executive decision to deal with it later.
So I probably missed the first point where how do you handle it because of unregistered user? Registered user I understand.
Mm-hmm.
How do you handle the unregistered user?
Oh, yeah, if the user is unregistered and keep clearing the browser cookie, then yeah, there's no way that we can connect them. And then probably for that user, the intent is he doesn't want to be tracked.
How many transactions per second you have the HBase?
HBase side, do we?
1,000, 5,000.
Yeah, a few. I think yeah, that's about
a few
right.
thousand per second. Yeah.
Were you using any solving strategies for HBase?
We are not updating, and we are actually using HBase not up to its full functionality. We're pretty much using it as just serving layer, like write once and read only. So we only load the data to HBase out of the batch pipeline, and then pretty much it becomes a read only.
So, what's the evolution, architecture evolution of Trig? Because the whole big data ecosystem is changing rapidly. What do you see as in the next 2 years? Maybe how are you going to change? What's the direction?
That's a good question. It's a little hard to predict 2 years down the road. But something that we can think about is, right now, one of the big direction is we are moving from the on-premise to the AWS or the cloud offerings. It's mainly because number one, we are seeing a growth in the user base, so we are seeing more and more data, and our colo data center space is limited. And then also we, on top of the same amount of data, we want to run different kinds of algorithm. We run a lot of different experiments. So that is one of the big direction there. Yeah.
So you have, in the architecture you talked about event API, pumping the data to Kafka, and from there branching off to real time as well as HDFS. Are you kind of storing small files, the small events as a small file on the HDFS, or you are kind of, how do you handle that HDFS problem of?
So first of all, we use KMU as the first part of engine. So basically, KMU kind of buffers a few minutes or maybe an hour of events. So it creates like one file for that period of time. So yes, we still have small files in the beginning. So we use a multi-sequence file for our scouting jobs, and then we also crash the files of the days before when we're ready, like when we know we're not going to append anymore. We crash them to bigger files, so that's how we avoid the problem. So it's like a long, like the fresher files are, we have more recent files and fewer older files. So.
May I ask another question?
Sure. We have 3 minutes.
I'm trying to understand the use case. Why do you need a real time, not a near real time? I understand batch and real time, understand the Lambda, but I'm trying to understand the use case in this kind of recommendation, personalization and recommendation system. Why do you need a really real time processing of the events? Why not a near real time processing of the events?
If you're really asking about is this real time versus near real time, we are doing near real time.
Okay.
If that, yeah.
Okay.
Because we're not like doing all this user trait building transactionally, like when user clicks one thing, we all of a sudden calculate that user's profile all together.
What's the typical gap when the events happen versus you process it?
It really depends because there are other like upstream dependencies, but generally when I click something on our site, on the production site through the browser and see and monitor in the Kafka side, I see about less than a couple of seconds of time that it takes.
Yeah, it's a few seconds, but no.
I'll ask the opposite question. Why do you need a batch layer at all? Why not just compute all these as they come in? Because there doesn't look to be a lot of interdependency between users, right?
Yeah.
You don't need to see the forest here. Each tree stands by itself, right? So
We have algorithms and models that go back over like a 3-month period, for example, and that's very hard to do in real time.
Sometimes we change our mind.
and they get implemented within the trait itself, within the user trait, or are you just building models?
So like, for example, when we calculate the user type to tell whether this user is buyer or renter, and then we basically look back what this user has been doing, and then obviously if the activity that this user has done today is more valuable than the same activity like 6 months ago, but how much different it should be. And then we continually like tuning our model, and then when we change the weight, then if we have batch layer, it's so easy. We just change the parameter there, and then by the end of the next batch cycle, all the user traits got updated. If not, we need to do major data cleansing, which is very hard. And also we make mistakes here and there, so we need to fix the bugs. I didn't say that.
We have 50 seconds. Yeah,
Right.
Last one.
This user trait, I feel that the user type example, probably 2 minutes buyer and renter, you probably want to also differentiate reflecting managers or agent type of users. So are you considering how to be able to increment enhance the profile to reflect those?
Yes. So again, this user trait data model is a simple subset of it because I could not fit in everything into here. There are some user traits that it's just text size is like more than 100 megabytes sometimes. Different user type, like more than the buyer and renter. Yeah, absolutely. There are people who are buyer and seller, and sometimes buyer and renter at the same time, so on and so forth. And then also there's investors, there are agents, so many. And we all know that by looking at each user's behavior. So it's agile process. At the end of the day, we tackle the bigger problem first, and then go down the list of our priority. Thanks, everyone.
Thank you, everybody. Thanks.